It's my pleasure to welcome Witold Sadowski from Warsaw.
Okay, thank you very much. I would like to thank the organizers for the opportunity to give a talk here. And I am also very grateful to Navier-Stokes for his talk because...
Microphone.
Oh, sorry. Because... Is it okay now?
No, turn it on.
This one. Is it better now? Yes. Okay, sorry. And I'm very grateful to Navier-Stokes for his talk because I don't have to mention many problems that he talked about, and now they are superbly explained. So I am going to talk about Lagrangian trajectories. Where should I? I don't think it's... No, I don't know. I can do it here, but it will be more difficult. Okay, I will do it here. So I will talk about the Navier-Stokes equations, and I will focus on weak solutions. So I will not talk much about strong solutions, which are known to exist for some time, but we do not know anything about their global existence. And in fact, strong solutions, they immediately become smooth. So when you talk about strong solutions, in fact, you talk about smooth solutions. I will only talk about weak solutions, and they have, in fact, very low regularity. So what we can say about the regularity in the space LWLS is this, that we can show that for weak solutions, they belong to spaces like that. And in particular, if you look at these numbers, if you take W equal S equal 10/3, then you obtain 3/2, and we know that a weak solution belongs to the space L 10/3 on the space-time domain. Okay, so if we compare it to the Serin's condition, we can see that we are just 1/2 away. So this 1/2 is worth $1 million, but it is a very difficult step to take, of course. And you can think that it is very close, but in fact, weak solutions, we don't know if they really possess some very desirable physical properties. So there is a list of some properties which you don't know about weak solutions. Of course, uniqueness, energy equality. It is not known if a weak solution is in L4, then you have energy inequality. Energy inequality, you know that you can construct weak solutions that do possess this property, but it is an open problem as far as I know whether any weak solutions satisfies this property. We don't have uniqueness, so maybe it is possible to construct a weak solution that does not satisfy energy inequality. And there are some strange examples, for example, by Serin, when you have a weak solution of this form, this function of space variable, it is a harmonic function, and then you have smoothness in space, but the function A of time, it can be very irregular. It is just enough with maybe L2, and we don't have any sensible regularity with respect to time. Okay, so the question you can ask if you think about particle trajectories is, what happens if you are given a weak solution? Can you construct Lagrangian trajectories? And the answer was given. So this is the classical formulation for the Lagrangian trajectories. And Foyash, Guidope, and Temam, they showed that we have also this additional regularity of weak solutions, and it allowed them to construct Lagrangian trajectories. So I will give the proper statement of their theorem in a moment, but let's just look at this picture that looks like Jackson Pollock's picture, but it was made by me. And we can see trajectories here. They may be quite irregular. So when we go back for a moment and we look at the previous slide, we can see that we look for Lagrangian trajectories that satisfy integral formulation. So they are absolutely continuous functions, but they don't have to be C1 functions. So you have this bunch of trajectories, and you can choose them because we don't know, maybe they intersect. If you just want to construct these trajectories, maybe they intersect, but you can choose such trajectories that you obtain a flow, which is a measure-preserving flow. And basically, that was the result by Feuillage et al. So you can choose them in a sensible way, so you obtain this nice flow. But the problem is that still, when you think about these trajectories, and they are not C1 functions, it is possible that they change rapidly direction. So they can, at some point, they can act quite crazy. And so this is the proper formulation of the theorem. This is, they are volume preserving, and we have this flow that gives us trajectories. And the question that I am interested in is, are these particle trajectories unique for almost all initial conditions? So if you choose an initial condition, do you have any freedom in choosing this trajectory? Or you just have to choose one, only one? You don't have any freedom, in fact. And another thing, how regular are these trajectories? So maybe before going to the theorem and the proof, let's just have a look at this example. We have a very nice flow here, and the function, yes, so we look for a solution of this problem, but of course in the integral form. And here we have smooth trajectories. What happens if we change the value of the function f only at 0? We consider a formulation which is an integral formulation. So we are allowed now to take a trajectory like that. So we change the function f only at one point, and we have a different result. So we have to, when we work with, I will work just with one representative. So because this function f, if we change it at one point, from the point of view of LP spaces, it is just the same function. And this example is was given by Nick Sharp, who was, okay, so this is a Nick Sharp example that helps us understand in what sense we consider this problem here. So we cannot consider it from a very general perspective. We cannot think about LP functions, but we just have to take one concrete representative of this one. And in fact, we will deal only with one class of weak solutions. So I don't know if this result that I am going to talk about, if it is true for all weak solutions, for example, satisfying energy inequality. But we have to work with suitable weak solutions. So these solutions, they satisfy local energy inequality. Now, I will not go into detail. So basically, you multiply the equation by u phi and you integrate. And you obtain an inequality in this way, and pressure is in L5/3 over space. And then you can prove, so this was a very famous result, of course, that the set of singular points, so such points where the velocity behaves in an uncontrollable way, is very small. And there are basically two results. The first one is more known, so that the Hausdorff parabolic, one-dimensional parabolic Hausdorff measure is 0, and in fact, the Hausdorff dimension then is no greater than 1. And you can also think about measuring the smallness of the set using the box counting dimension. And then you can prove that it is less than 5/3, in fact. There is a better result. 5/3 is very easy, in fact, to prove, and I will show it. Igor Kukavica showed recently that this box counting dimension of a singular set is in fact less than, so 1666, it would be 5/3, so it was something like that. In space, yes. I will just give a definition right now, what I mean by a singular point. So we consider it in the space-time domain. We take a point in space-time if we can find a neighborhood on which U is continuous, then it is a regular point. If we cannot find it, then it is a singular point. And this famous result was that we can cover the set of singular points by a family of cylinders. So when we look at this picture here, we can see this red set of bad points, and we can cover it with the countable family of cylinders such that they are r squared is the length in time, r is the radius of the ball in three-dimensional. So the first result that we obtained was a conditional one, and we proved that if a weak solution, we know that a weak solution belongs to this space, but if we assume that instead of 1 we can take 6/5, then these trajectories are in fact C1 functions. So I will show very briefly what the proof was. So we wanted to show that if we choose an initial condition and we construct this trajectory, then we must avoid the set of bad points, so these singular points. And this is the theorem that says so. And the proof was quite easy. If we consider a cylinder, we can also consider a ball at a given time, at a given slice time, such that you have to be in this ball if you want to hit the cylinder between time tk and tk plus rk squared. Why? Because we have a bound on the maximal distance that a trajectory can travel between time tk and tk plus rk squared. Yeah. So these are capital RK, they show how fast you can travel between time tk and tk plus rk squared. And then we were able to show that if we look at these balls, and we have to show that the total volume of these balls can be as small as we wish. And we can do it if we have this additional property, this 6/5 instead of 1. And then you can just use Hölder's inequality. Yeah? Because we are able to, of course, small rk, we control very well, because this is the Caffarelli-Kohn-Nierenberg result. And we want to use somehow here, you have to show that this sum is also as small as we wish. And we can do it by Hölder's inequality here, because we integrate between tk and tk plus rk squared. So here we obtain rk squared, and they appear here. If we cube it, then we obtain the sum which must be as small as we wish. So this was a simple idea, but it was somehow not nice that it was a conditional result. What we really want is to obtain the result that if you really take a suitable big solution, then the trajectories are C1 functions. And okay, because in this case, if you avoid this set, then it is easy to show that you have a C1 functions, because you just take a point. So this is the proof of uniqueness of the trajectories. If you take a point which is a regular point, then you have results about regularity of U in the neighborhood of such a point. So of course U is continuous, but you have also Serin's result, which says that if you consider time slices, then U is in fact on these time slices is regular is smooth in space variables, and you have uniform bounds on the norms of du and other derivatives in space. Okay, and then it was possible to prove that you don't need, in fact, any additional conditions. You can just take a suitable weak solution. So, of course, we take this particular representative that is smooth around regular points. Yes. And the idea was to use the box counting dimension instead of Hausdorff dimension. So the box counting dimension is, you have a set. There are many different definitions, but the one we used was that you consider what is the maximal number of balls that are centered at points of this set and are of radius r. So given r, you find the maximal number of balls that are centered at the points of this set, and they are disjoint. So this is the formal definition. We always have that the box counting dimension is greater than the Hausdorff dimension or equal. And it is quite easy to show that the box counting dimension of a singular set is no greater than 5/3. And again, you use this property that U belongs to LP L10/3 over space-time domain. And when you have a singular point, then you show that something like that must happen in some neighborhood. This is the cylinder. This integral cannot be too small, and this smallness is measured in terms of r. So if you have many such cylinders like that, more than r to minus 5/3 minus some delta, then the right-hand side, if you sum all these cylinders, the right-hand side would tend to infinity, and this integral that has to be finite would not be finite. Of course, there's also pressure involved. You can. Okay, so using this fact that the box counting dimension is no greater than 5/3, you can show that, in fact, these trajectories avoid this singular set. And the idea is to divide time into equal intervals, and on each interval we find the maximum distance that the particle can travel. So these are delta 1, delta 2, delta 3, and so on. And we consider on each time slice, because we have these times here, we consider time slices, and on each time slice we consider a delta k neighborhood of the projection of the singular set onto this time slice. So we have these bed points, we project them onto R3, and we take delta k neighborhoods. And then it is just enough to use the fact that the integral of u L infinity is finite. So this is the idea. We take the neighborhoods, and we have a way of measuring, if we know that the dimension of a set X in Rn is smaller than D, then for any D prime greater than D, we have a bound on the measure of a delta neighborhood. So in this case, we can show that the total number of this, the total measure of these red balls and then the total measure of these blue balls can be bounded above by C delta 1 to 6/5. For example, there are many other numbers like that. C delta 2 to 6/5, and so on. And then we use the fact that the flow is measure preserving, and simple calculations so that we just use the fact that this integral is finite. If we add all these integrals, we obtain this norm. This is finite, and this has to tend to 0. So we can see that the measure of initial conditions that give rise to trajectories that intersect this set is as small as we wish. So this is the idea. So these are the papers that are related to this question. Eisenman considered this problem, and it was his idea to use the box counting dimension. We discovered it later after proving this conditional result. And of course, this famous paper by Caffarelli, Kohn, and Nierenberg, the other by Foyas, Guillaume, and Temam that I talked about, and these two papers. So there are some open problems. We know that these trajectories are C1 functions, but can we prove something more. Because it may be interesting to prove some regularity in Helder spaces. And in some cases you can, so this is related to regularity in the neighborhood, regularity of U in the neighborhood of a regular point. So the problem is regularity with respect to time. And not much is known about this. So in particular, as far as I know, it is an open problem whether UT is continuous in a neighborhood of a regular point. You can show some results when you consider the whole space. You can show that you have regularity like that of U, C0, for gamma less than 1. But only if you consider the whole space. There are some results like that. Another question, what happens if we consider just weak solutions satisfying, for example, energy inequality? And then what has it to do with the global regularity problem for the Navier-Stokes equations? So what can we obtain from considering Lagrangian trajectories to deduce something for the regularity of U? And these are open questions. Thank you very much.
Okay, questions?
What can you say if the flow is compressible?
I don't know. I didn't consider this example, and I don't think that you can obtain these results.
How do you know the projection of a singular on the time slice is a ball rather than a line?
So we know that this set, this singular set, is very small, and what we know is that the box counting dimension, when we consider it in the 4-dimensional space, is less than 5/3. So you project it, and then if this is the set S, and let X be the projection of S, then you can, because projection is a Lipschitz mapping, then you can prove that the box counting dimension of X is less or equal 5/3. Yes, 5/3. And this is enough because these balls that I considered, it was a delta neighborhood of these points here. So I didn't claim that what is the shape of this set when you project it, but you know that the box counting dimension is less than 5/3, and then you can say something about the delta neighborhood of such points when delta tends to 0, because this is important, when delta tends to 0.
On the back.
Yeah, just to add to, can we maybe close the door there because it's so noisy? Just to make a comment about this line of research, just to indicate, even though it looks like so abstract, whatever, it's really very much in the heart of matters. A comment on the Caffarelli-Cohen-Nirenberg showing that the singular set in space and time is less, the Hausdorff dimension less than 1. It automatically shows, like, for example, the result I mentioned yesterday by Lagrangian comes as trivial consequences of that. Why? Because if you have 1 point singularity, because of the symmetry, you have a whole circle of singularity. And the dimension of the circle is 1. And we know the singularity set should be less than 1. Therefore, it's not possible to be singularity in axisymmetric case. It comes as a trivial. So this is not really just general abstract nonsense. There are some consequences could come from that, just to basically to enforce this line of research.
Well, on a positive note, I think it's a very good point to end this morning's session. So let's thank Witold and all the speakers again. Thank you.